University of Washington, where he's working with Shyam Kakagde and Imo Todorov. Before coming to UW, Aravind was at IIT Madras, where he got the Best Undergraduate Thesis Award. Arvind's research is around reinforcement learning, meta learning, and dexterous manipulation. He has done some exciting work on the interface or the intersection of model-based and model-free learning. And I'm very excited to hear about what Aravind has to say. And he has received multiple awards, including a JP Morgan PhD fellowship and a Best Paper Award from IEEE SIMPAR. So with that, Aravind, take it away. Super excited.
Thank you so much for the kind invitation, Pulkit, and thank you everyone for joining. It's such a pleasure to be here and give this talk. So I would like to begin my talk with a robot demo that is about a decade old. This is the PR1 robot, which is being teleoperated by a human to perform a variety of household tasks. This demo, to me at least, suggests that for over a decade, we have had physical hardware capable of performing many of these tasks, but we have not been able to do them autonomously. If we can develop good learning algorithms so that we can replace the human teleoperator with these algorithms, then we can make the robots autonomously accomplish these tasks. Having better sensors and hardware can potentially simplify the algorithm design process. But nevertheless, it is clear to me, at least, that we are lacking primarily in terms of algorithmic advances in robot learning. So I'm kind of working under the assumption that algorithms are the primary bottleneck in robot learning. And my PhD work has focused on new algorithms to make robots solve a variety of different tasks. And I'm excited to share some of those with you today. So to make algorithmic progress, we can abstract the robot learning problem into a question. How can we enable agents to learn many tasks with a modest amount of experience per task? To accomplish this, I believe we need to think about at least 3 pillars. We need agents that can learn any given task with as little experience as possible. And this is essentially sample efficient reinforcement learning. Secondly, even the most efficient reinforcement learning algorithms may not be efficient enough when learning from scratch. Furthermore, it might be very hard to communicate human priors and preferences in the form of a simple reward function. Thus, we need algorithms that can also utilize human experience in addition to autonomous learning. And this is the subject in apprenticeship learning or imitation learning. And finally, I believe the key to unlocking the potential for efficient learning and creating AI agents with very broad capabilities is through reuse of experience from other related tasks and datasets. This is a broad category and involves like many different fields like offline reinforcement learning, simulation to reality transfer, meta learning, and so on. Essentially, we want to be able to accelerate the learning in any particular MDP using data or experience from other related MDPs. I think it is also key that we strive for a solution paradigm that can integrate all of these pillars together instead of working on separate approaches for each of these components by themselves. So I am personally a big fan of model-based reinforcement learning. And in this talk, I hope to share some of my recent work in model-based RL and also try to convince you that model-based RL can indeed support and seamlessly integrate all of these 3 different pillars. So just to briefly recap, model-based reinforcement learning involves essentially learning a world model using all the available data so far, and then using this world model for policy learning. I find model-based RL to be very appealing for a few reasons. Firstly, it is highly modular and extendable. We can readily borrow any advances from supervised learning or self-supervised learning in building world models. And this is like an aspect of deep learning where we have made the most progress, in my opinion. So we can directly port advances from like very advanced areas in deep learning and directly use them for our purposes. Similarly, once we have a world model, we can borrow many advances from decades of work in motion planning, dynamic programming, trajectory optimization, and so on. Secondly, the world models are task agnostic, which make them very easy to pool data from multiple different tasks and jointly learn a world model. In particular, suppose we consider scenarios where we have multiple different tasks in the same complex environment, let's say in the home of a user. We can pool all of these different data from multiple different tasks. And since they all share the underlying physics of the world, we can hope to learn a broadly competent world model. We also have strong existence proof for success of model-based RL through humans. Cognitive science literature suggests that humans build models of the world in early stages of cognitive development without any particular task in mind, like this baby in this particular video, which is essentially exploring the world without any particular task in mind, but is constantly building up a world model. Subsequently, these world models are used for mental simulation when faced with like specific downstream tasks. So overall, to me, all of these factors together suggest that model-based RL is a very interesting paradigm to work on, and also has the potential to combine aspects from all of the three pillars that I mentioned. Of course, the open question is like, how do we develop good algorithms for model-based RL? And I hope to share some of my advances in that particular realm. So to start off, let us first look at how model-based RL can be useful for offline RL. And just to refresh, offline RL is the setting where we need to learn the control policy using only a pre-collected data set of interactions with the environment. We don't get to repeatedly interact again and again with the environment like we can do in conventional reinforcement learning. Since we separate the data collection process from the policy learning process, we can also sidestep any safety concerns due to autonomous exploration, which is like one of the major advantages with offline learning. In addition to, of course, the capability to reuse like a lot of pre-collected data. And this offline data can come from a combination of different sources. Like it could include historical data sets through any historical policies that we may have deployed. It can also include like some safe hand-designed policies where we are guaranteed to like not break the robot or damage the environment, but still like be able to collect data that is helpful for the task. And it can also include like human demonstration, let's say through various forms of teleoperation. In practice, we may like perhaps occasionally go and collect like a little bit of additional data from the environment as well. But really the bulk of the work is going to happen in data-driven policy learning. And that's really the focus that we want to, that's the aspect that we want to focus on. And so overall, the use of offline data sets can reduce the interaction sample complexity, address any safety concerns, and also expand the overall applicability of reinforcement learning. And the central question in this research paradigm is how do we design algorithms for learning policies from only static offline data sets? And this question is particularly challenging when compared to interactive RL because of two major challenges. And these are distribution shift and extrapolation error. So suppose through an example, let's say we have, we want to learn a policy for autonomous driving, and we have like lots of data of cars driving on the roads. Since we have data only on the roads, an agent might erroneously predict that all of the world is just like a road. And in order to drive somewhere faster, you just have to keep accelerating. That is clearly not the case. And if we accelerate without understanding that there are roads and like there are cliffs, we can really fall off a cliff like in this particular example here. So how can we overcome this challenge? Well, one possibility is to adaptively collect like additional data. For example, if we crash a few times and collect data about those crashes, we can perhaps learn how not to crash. However, this additional data collection is not possible typically with offline RL. And furthermore, this approach of essentially crashing to learn how not to crash doesn't seem particularly appealing and scalable. An alternate approach is to perform regularization to communicate to the learning agent to respect the support of the data distribution and not stray too far from it. This regularization approach in one form or the other is crucial for any offline RL algorithm. And prior work has concentrated primarily on model-free RL algorithms based on like regularized variants of Q-learning and actor critic algorithms. And they were the state-of-the-art algorithms like before our work. And like there, unfortunately, not much attention was paid to model-based algorithms for offline RL. So with this backdrop, like I would now like to present one of the algorithms that we developed for model-based offline reinforcement learning. and we call this algorithm model. So firstly, let's start with the naive model-based RL approach, which is shown on the bottom left. We will learn a dynamics model using the offline dataset and optimize a policy using the learned model. And that's like just like the conventional, like run-of-the-mill, like model-based reinforcement learning. And this approach, unfortunately, will not work both in theory and in practice due to distribution shift and model exploitation, like I just described. And this is what we aim to address in our algorithm model by incorporating the key idea of pessimism or conservatism in the face of uncertainty. So we will first train an error-aware pessimistic MTP model. And this has the special property that for any policy, the value in the pessimistic MTP is an approximate lower bound for the true value. And that makes the pessimistic MTP a very good surrogate for the purposes of policy evaluation and optimization. The overall flow diagram of model is shown in the bottom right. We learn an approximate world model using the dataset, similar to like a naive approach. And then we construct this pessimistic MDP, and I'll describe the details shortly. And once we have this pessimistic MDP, we will optimize a policy on this pessimistic MDP. And this pessimistic MDP essentially provides the regularizing effect that we need and allows us to succeed. And the main difference between model and a naive approach is really, instead of optimizing the policy directly on the model M hat, we will optimize the policy on the pessimistic MDP MP hat. So any questions at this stage, like before I get into more details about this particular project? Cool. And also just like feel free to stop me anytime and ask questions. Like we can make this like as interactive as possible.
Yeah, I mean, if you're more comfortable putting the questions on chat, please do that. I'm happy to read out the questions to Aravind. So please feel free to speak out or put them on the chat.
Cool. So the idea behind this pessimistic MDP is actually very simple, and it's essentially to partition the state space.
MDPs. Oh.
Sorry, I think that was someone's mic just got unmuted.
I see. No worries. So the idea behind the pessimistic MDP is actually pretty simple, and it's just to partition the state space into known and unknown regions. So I'll describe this through like an illustrative example. So suppose this is the state action space of the MDP. And let's say the blue dots represent the data points that are in the support of the data set. Then the known regions described in green are those regions where we can guarantee that the learned model will be accurate. And in particular, we are going to consider like total variation distance as the metric for guarantee. Like, and I'll describe like a practical algorithm soon, but I want to describe first the idealized construction using a theoretical framework. So the known regions are those regions where we can guarantee that the learned model P hat is no more than alpha away in total variation sense to the true unknown model P. And any place where we cannot make such a guarantee, we're going to be conservative and call that unknown. Note that this is like a one-sided guarantee, meaning that even in some of these unknown regions, our model can actually be pretty accurate. But because we cannot guarantee that the model will be accurate, we will be conservative and assume that it is unknown. So this describes the partitioning of the state space into known and unknown regions. And whenever we are optimizing the policy in this pessimistic MDP, if the agent wanders into the unknown region in the pessimistic MDP, we will force a transition to an absorbing state halt where it will perpetually remain and continue to get very low rewards. Essentially, the intuition is that we are penalizing the agent for going into these unknown regions. And since policy optimization likes to avoid low rewards, it will avoid going into unknown regions and stay within the known regions where we know that the model is pretty accurate. And as a result, we can avoid this model overexploitation and this distribution shift issue. And we can sort of formalize this intuition into the form of like a more concrete theorem. Suppose we learn a near optimal policy in the pessimistic MDP, then the suboptimality compared to an optimal policy pi star is essentially bounded by two terms. The first term is a local modeling error term and depends only on the error within the known regions. Note that in a naive MBRL kind of an approach, the suboptimality will be governed by the worst case model prediction errors, whereas in our particular formulation, it depends only on the error within the known region. The second term is related to what we call the hitting time, which is a new quantity that we introduce, and it is the first time that the optimal policy will enter into the unknown region. Intuitively, we can think about it as our view of the world is limited after the agent crosses into the unknown region, and anything beyond the unknown horizon, we really can't say anything concretely about it. So the first time that the optimal policy enters into the unknown region, that's where we have to stop competing with the optimal policy and assume the worst. And note that there is a trade-off between the two terms. If we reduce alpha, then the first term will become smaller and smaller, but we will also reduce the hitting time because we reduce the size of the known region. And as a result, the second term will start to blow up. So we can interpret it as if the optimal policy actually does not visit the unknown region and stays within the known regions, then we are as good as we can hope to be because the second term will disappear. The hitting time will be infinite and we are only governed by the first term. In contrast, if the optimal policy actually goes into the unknown region, then we know for sure that we really cannot compete with the optimal policy using the data set that we have because there is a clear support mismatch between the optimal policy and the data that we have. And the salient features of the theoretical resource is that it depends only on the accuracy in the known states, like I mentioned. We introduced this new notion of hitting time for sharper analysis. And most prior works can only provide theoretical guarantees when the support is overlapping between the data set and the optimal policy. Whereas we can provide guarantees like for any data set and for any optimal policy. And the most interesting aspect is that this actually matches a lower bound for offline RL. What this means is that no offline reinforcement learning algorithm, even a yet to be discovered one, can perform better than moral for all problem instances. So this is like among the strongest theoretical guarantees that we can hope for in like hard instances like offline reinforcement learning. And it's actually very interesting that a model-based algorithm can get this particular minimax optimality guarantee, whereas like no model-free algorithm that I know of can achieve this minimax optimality guarantee. So I know that this is like a lot to parse, so I'm very happy to take like a couple of questions here if there are any doubts.
So Aravind, how do you define known and unknown regions? Is it based on visitation? Is it based on whether your dynamics model is accurate or not?
And yes, so that's a good, yeah.
Does the bound depend on how you define known and unknown?
Yes, that's a very good question. And I want to first describe kind of the ideal theoretical notion first, and I'll describe shortly how we do this in practice. So for the idealized like theoretical interpretation, you can view the known regions as where our dynamics model is guaranteed to be able to predict the next state accurately. So it is really in terms of not like visitation distributions, but in terms of our ability to predict the future. And this actually subsumes a visitation distribution because you would presume that if the model is high capacity, then if we have data in some region, then we can actually predict accurately in the vicinity of where we have the data. And where we may not be able to predict accurately or where we do not have the data, although we can actually still be able to predict beyond where we directly have like visitation support. And that's because if we can learn good representations, then that might enable us to even do a little bit of extrapolation. So that's kind of why we view it primarily in terms of the predictive capability of the model, which in some sense is like really broader than state visitation, because wherever we have like high degree of state visitation, we know that the model will be pretty accurate. And even in those regions where we do not have very high state visitations, we could still be pretty accurate because we learned very good representations.
So to know if something is known or unknown, right, you'll have to take an action and then measure the error, right? So if something is unsafe, then you would end up taking that action, right? So how would you distinguish between known and unknown without taking the unsafe action?
Yes, so loosely interpreted as like just like an augmented state action space. So we have, in some states, we know the consequences of certain actions. Then we will know with high probability the consequences of similar actions. And similarity is like appropriately defined on some metric space. And that depends on, like, for example, in like a continuous control kind of a problem, then we know that like if we take like consider some navigation example, then we can drive straight. Suppose our action is like to drive at like a 10-degree or a 20-degree angle, then we can pretty confidently predict like what that is going to be. But we may not be able to like predict what's going to happen in reverse, for example. So it depends sort of on, is there like some metric space that can support a notion of generalization? But this is like really coupled with the problem of generalization and learning like generalizable models. And perhaps like when I describe the practical algorithm, like things might be a bit more clear.
Okay, I think let's see as a question.
Can I ask a question, if I can?
Yes, go ahead.
Is there any connection to robust MDP? So it seems to me that there may be some connection. I mean, you seem to introduce a total variation type of constraint on the probability model. If you can make any comment to that, would be great.
Yes, so this is definitely can be interpreted as an instance of like robust MDPs. Like typically in robust control or robust MDPs, the set of models that we want to be like robust against or guard against, they are not typically data driven. So we do not like use the data to inform what is the confidence set, for example. Those are typically handed down to us, and we just try to be as risk averse as possible. Whereas here we are actually using the data to, in some sense, inform what is the set that we want to be robust against. And once we have that, then we are running like a robust control style algorithm.
Well, yes and no. I mean, there is more recent work on distributionally robust and so on, that where they use sample paths to generate nominal distributions and then define uncertainty sets around those nominal distributions.
Yes, so that is true. So maybe I would take a step back and view this primarily in the context of offline RL. So maybe the solution concept has like some similarities to like robust MDPs or robust RL. But the goal is really not to provide like a new algorithm for solving robust MDPs. It's rather to solve like offline RL. And maybe the approach that we take has like a very strong parallels or similarities to robust RL.
All right, thank you.
I was just curious, can you go forward to the slide with the bound on it?
Yes.
So is there some, so what I realized based on Pulkit's question is, of course, we won't know for sure what how accurate the transition model estimate is. So is this bound for the case where, I mean, does it include a kind of a term for the fact that there's actually uncertainty in our estimation of whether we're certain about the dynamics in a state?
I see. So yes, so you can interpret alpha as our degree of uncertainty. So maybe interpret it as if I can, like, if I produce to you an MDP where I tell you that in certain regions of the state action space, this model that I'm giving you is alpha close to the original MDP. Suppose I give you that, then yes, this theorem is valid. Now the question is, how do we get an alpha approximate MDP?
Right.
And that's kind of where like all these like concentration inequalities and typically like finite sample issues come in. So if you look at the theorem bound, for example, there's no description of what is the number of samples used or something like that. So this is like, given an alpha approximate MDP, this is what we can hope to get. Now, how many samples do I need to get an alpha approximate MDP is a finite sample issue, and we don't really analyze that over here. But typically, it's like the standard statistical inequality. So something like square root of like 1 by log over epsilon, or square root of n by log over epsilon would be about like what alpha would be.
Right. Okay. So, but then you have also a kind of, you might have a mixing problem or something. I mean, it might be actually take you quite a few examples in order to get enough samples at any given state in order to be sure about it.
Yeah. So that's where we are calling this as known and unknown, right? Like, so suppose we have like lots of samples in a particular state, then we will call it known, and then alpha will take care of it. If we do not have enough samples in some state action space, then we will simply call it unknown, and that the second term in the bound, the one related to hitting time, will handle those state action parts.
Good.
Cool. So I guess in terms of a practical version of this algorithm, like we do like a fairly common approach to uncertainty quantification in recent times, which is just like using ensembles of dynamics models. So we will consider an ensemble of different dynamics models, all parameterized by neural networks. All of these networks will be initialized independently with different initial parameters, and they will all be trained on the same data set, but using different mini batch sequences. And that we will also add like a different randomized regularization to all of these members in the ensemble, so that the predictions or the desired target predictions for all of these members are not identical, although they are centered around what is available in the data set. Now, wherever the models agree, they will agree only because there is the data forcing them to agree. In places where we do not have any data, there is no reason for the different networks to agree. And because we add the small random regularization to the networks, they will tend to disagree. So simply by looking at the agreement or disagreement between the different members in the ensemble, we can know if a particular state action pair is known or unknown. And based on this disagreement, we perform this partitioning into known versus unknown that I described earlier. Once we have this partitioning, we can employ essentially any reinforcement learning algorithm to learn a policy in this like learned pessimistic MDP. We simply use like standard iterative policy optimization algorithms like natural policy gradient or PPO to solve this. And the nice aspect is, because it only requires samples from the learned model, we can easily use ensembles of learned models as well as different probabilistic models in the ensembles. Like for example, if you want to use like a back propagation through time approach for optimizing the policy, then we may be forced to consider deterministic dynamics models or specific types of probability distributions that we can still differentiate through by using various reparameterization techniques. But if we use a sampling-based optimization method, then we have a lot more flexibility in the kind of model parameterizations that we want. And as a result, we simply stick to some of these sample-based policy optimization algorithm largely for convenience. And once we have these trained models in GPUs, we know that neural networks can act as extremely fast simulators when run on a GPU. So we can generate thousands of trajectory rollouts in parallel on a GPU. And as a result, like get a very low variance gradient estimate and typically optimize the policy in less than like a few hundred iterations. So overall, in terms of resource, we consider 4 different environments that are part of the standard OpenAI GEM locomotion tasks. For each environment, we consider 5 different data logging policies. And these data logging policies have different qualities. For example, these are completely random. Some of them are very close to expert level performance, and others are at various intermediate stages. And this is really to emulate the kinds of real world applications of offline RL, where think of something like a factory automation or chemical process control, where we have some potentially hand-coded policies controlling various chemical plants, and we have like days or months of data from this process. and these are from a suboptimal policy. Then we can use this particular data set to try to produce an improved policy. So overall, just to recap, we have 4 different environments, 5 different data sets per environment. So we have a 20 domain benchmark. And what we observe is that our algorithm model gets state-of-the-art results in 14 out of the 20 different environments. And the next best algorithm, behavior regularist actor critic, a model-free algorithm, gets state-of-the-art results in only 5 out of the 20 domains. And what is also exciting is that whenever our algorithm gets state-of-the-art results, it beats the next best algorithm by a huge margin. Whereas whenever behavior regularist actor critic gets state-of-the-art results, model is still very competitive, like almost at 90% to 95% mark of what behavior regularist actor critic gets. And model also has this other advantage compared to model-free algorithms in terms of computation time. So since we can clearly separate model into 2 phases of like learning a dynamics model and then using the learned dynamics model for policy optimization, we really have very little computation costs. Like learning the dynamics model using a given data set is standard like self-supervised learning. And we know we can do this like within like a few hundred epochs. So it's no more than half an hour or so when we have like a good GPU. And similarly, once we have a learned model, it can act as a very fast simulator, and we can optimize a policy in fast simulators like very, very efficiently. So overall, model takes no more than an hour of training time for these tasks. Whereas the model-free algorithms, because they have to solve this very complicated fixed point optimization and Bellman residual minimization, have to use like extremely small learning rates, have to have target networks with moving average weights, and just like do hundreds and hundreds of epochs over potentially a very large offline RL data set. And as a result, they are computationally very, very intensive when compared to model. So overall, like model gets both like very good empirical results and also achieves it with very little computation. And just like provide some intuition about these tasks and results. On the left, we have trajectories from this like locomotion data set where the robot has to like hop or like the quadruped has to like move around with 4 legs. And on the left are the offline trajectories from the offline data set. And we can clearly see that the gates are not that good. They're not terrible, but they're not great either. And that is like representative of many real world applications. On the right is the final output of the model policy. And we can see that the gates are significantly good. And in fact, in many of these cases are very close to the optimal gates. Like even if we could collect like mountains of interactive data with the environment, we really cannot produce a policy much better than the policy on the right. So even with highly suboptimal offline data, we are able to learn a near optimal policy with our algorithm. So just to summarize this part of the talk, there are 3 aspects that we really care about when dealing with offline data sets. The first is offline policy evaluation. So I give you a data set and I give you a policy, and the task is to evaluate how much reward will this policy get using this offline data set. In a model-free approach to do this, we really have to solve a very complicated fixed point Bellman residual minimization problem to get an estimate of the value function. And even after we do this like very complicated exercise that has to be repeated for every different query policy that I give you, there is no guarantee that the learned Q function would have anything even remotely resembling the true Q values if you were to execute the policy in the environment. And there have been like many papers where you can see that there's like absolutely no correlation between like learned Q functions and the empirical ground truth Q functions. Like a case in point being like the DDPG paper where they have like a plot showing a huge discrepancy. Whereas in a model-based method, like in particular model, offline policy evaluation is super simple. Simply take the policy, roll it out on the learned pessimistic MDP, and I can give you a very accurate estimate of what the, and like in particular, if the policy does not visit the unknown region, then with very high confidence, I can accurately predict the value of the policy. And if the policy actually happens to go into unknown regions, then I can also confidently tell you that I cannot actually evaluate, or in fact, no algorithm can evaluate the value of this particular policy using the provided data set, because there is just like simply too much of a support mismatch between the two. In terms of policy regularization, again, model-free algorithms are forced to directly regularize in the policy space. So they have to constrain the policy that they are learning to not to take actions too different from what is there in the data set. Whereas in model, we can regularize in the space of state visitation distributions and not in terms of policies. So the class of policies that we can consider while optimizing is much richer in a model-based algorithm, because we can still consider policies that potentially take very different actions than what's there in the data set. But as long as we can confidently predict that those different actions still lead to states that are in the known regions, then we can still consider those state action pairs. So the set of policies that we consider in model-based is much richer. And finally, in terms of generalization, again, because model-based algorithms can train on wider set of state action pairs, and not just the support of the state action pairs in the data set, but rather essentially train on all state action pairs within the known regions, we can hope that model-based algorithms will also have broader generalization capabilities. So just to summarize, like model achieves state-of-the-art results. It has like a minimax optimality guarantee, which no model-free algorithm has. And it's a very scalable and computationally efficient approach. So again, at this stage, I'm happy to stop and take a couple of questions, and then I'll quickly highlight some of the other projects that I've been working on recently.
So it's one of the main bottlenecks in applying model, how accurate your uncertainty model is. Like if you're working from high dimensional observations.
Yes, that's a very good question, and that's like the question of interest, right? Like, so the state-based case is good, but in practice, we really have to deal with high dimensional vision. We have a project that is ongoing, and hopefully in a week or so, it will be on archive, where we actually get like very promising results, like both like high dimensional, like essentially RL from pixels in simulation, as well as like real world robot experiments. And I'm actually very pleasantly surprised how well this works. So yeah, unfortunately can't share the results right now, but like maybe in a week or so, it will be on archive.
Thanks, Aravind.
So even in, yeah, I had a question. So even in state-based case, I was wondering, how model would do on higher dimension when like the state dimensions are slightly higher. For example, in case of kitchen tasks, or in case of Android tasks, which are also like part of D4RL benchmark.
Yes, that's a very good question. I unfortunately don't have the results on the slide, but it works great on the Android tasks. And I'll in the remainder of my talk, I'll show some results on the offline on the Android tasks. They are not like strictly with model, but they are with very similar algorithms, and you can hopefully get a sense of how well it works. And offline, I'm happy to like point you to like sections of the paper where we consider like more high dimensional tasks as well.
That sounds good. Thanks.
So it seems to me that also if you are doing model-based with, say, pixel observations, say high-dimensional observations, like papers like Dreamer, they typically only bootstrap the model in the latent space. So many papers, I know there are papers also do predict the true images, like simple. But it seems to me it could be a promising direction to only bootstrap in the latent space.
Yes, that's basically what we do in that paper that I mentioned.
That's what you do. I see. Yeah, that is what I'm wondering. Like, I think it's a better approach, and yeah. So I want maybe hear your comments on like whether to bootstrap only in the latent, or like what is the trade-off between only in the latent or I also bootstrap in the actual observation space.
Yeah, that's a very good question, and in a sense, like going back to offline RL, like this is like strictly harder than just like vision based RL, because not only do we have to predict like future, like, and ideally we have to consider something like a reconstruction based like loss to train our models at some level, regardless of whether they are latent or not. And like in offline RL, not only are we like hit with this high dimensional prediction problem, but we are also hit with predicting uncertainties in high dimensions, and that's like much, much harder. So what we end up doing in that particular paper is essentially representing the uncertainty in the latent space, and that like we have a particular way to do it that works quite well, and that is like both computationally tractable, like because like we could not actually run like confidence interval style algorithms like directly in the image space. So we were in some sense forced to, like for practical reasons, forced to go into low dimensional spaces or the compact latent space. But we can actually represent uncertainty pretty well in the latent space, and like that works pretty well in practice. So
Can I have a quick follow up? That is, so I think in the row state based in model-based reinforcement learning, you typically capture the uncertainty using a normal distribution, for example, the most. And so in your paper, in your new paper, how do you capture the uncertainty? Is normal distribution still a good bias to put in?
So there are two aspects of the uncertainty. Like one is something that I wouldn't actually call uncertainty. It's more to do with just like having a probabilistic model. So typically we will try to predict what the mean of the next state is, and then there will be like a Gaussian noise around it. And the Gaussian noise around the mean that we predict isn't really uncertainty. That's just the choice of the probabilistic model. The uncertainty would actually be like, are we predicting the mean correctly, and are we predicting the standard deviation correctly? Like that constitutes uncertainty. And that uncertainty is typically captured using model ensembles. So I would separate the probabilistic part, which is just like a consequence of having a probabilistic model, with uncertainty of those probabilistic models, which is typically captured using parametric uncertainty.
Yeah, thank you very much. I'll follow up these in our one-on-one. I'll save more time for the talk. Thank you very much. Yeah.
Sure. Yeah, so just to quickly run through the rest of my talk. So so far I presented like a model-based approach that is applicable in the offline setting. A natural question is like, if we can collect like some more data by interacting with the environment, can we still use model-based methods, and how would we go about doing it? And there are two views to this. Like one is to view offline RL as a surrogate for online RL. So iteratively, as we collect more and more data, we will be just solving a different offline RL problem as we accumulate like more and more data. And the second view is that model is just like an intermediate step in providing a low variance policy gradient. And the goal is just to like improve the policy using the gradient based algorithms. And the model is just like a means to the end of producing the gradient. And these two views are actually dual approaches. And if we, in our particular work published at ICML, we actually show that by taking a model-based lens for these two different views, we can actually show a very deep connection and similarity between these two. So unfortunately, in the interest of time, I'm skipping the details, but I'm happy to go over them in our individual interactions. So essentially, we formulate model-based RL as like a game. And we prove that by solving this particular game, we can actually have like a near optimal policy in the environment. So like just like an informal version of the theorem is that once we set up a model-based RL game, and unfortunately I don't have time to go into the details, but once we have this game, then solving this game would allow us to recover a very good policy for the environment. And as a result, we can now employ game theoretic algorithms for model-based RL instead of like purely optimization-based algorithms. And these algorithms tend to have like a lot of advantages. The primary advantage is sample efficiency. So what we find is that our algorithm shown, like two variants of our algorithm shown in blue and green, are substantially more sample efficient compared to like a variety of other baselines, including like soft actor critic, TD3, PETs, and so on. So all of these are like state-of-the-art algorithms at the time that we published the paper. And we see that there's like almost a 10x efficiency improvement by using these game theoretic algorithms. And these efficiencies are not just like small improvements that that are like subject to like hyperparameter disclaimers, but rather these are like huge improvements that actually go to the point where we can run these algorithms directly on hardware. And here's like a very simple demo where the task is to make this 3-fingered like robot claw rotate the valve on the bottom to match the orientation shown on the top. And what we find is that in a matter of I think 20 minutes of real world training time, we can actually solve this task like without any priors, like by directly running it on the hardware. Whereas like other algorithms like soft actor critic or like on policy algorithm take like significantly longer, like orders of magnitude longer to solve this task. So just like a simple demo to illustrate that our progress in model-based RL has gotten us to a point where by not like really restricting the capacity of the models, like we are not like using Gaussian processes or just like estimating like 10 or 20 different parameters or something like that. We are like actually training like flexible neural network models for both the dynamics as well as the policy. And our model-based algorithms are good enough to the point where we can directly run them on hardware and get like pretty good results in just like 15 to 20 minutes of training time. And just to kind of also echo Anurag's point, like we also tested some of these algorithms on more high-dimensional text stress manipulation tasks. And these tasks are particularly challenging for model-based algorithms because since we update the policy by like going essentially through the model has to be able to capture all the intricate details of context in these tasks. And what we find is that like it's pretty well known that model-based RL can work well for like smooth systems, but these are like highly context-rich tasks where the context can change like very rapidly. And still, like our model-based algorithms are good enough to capture the model-level details, and these models can enable us to learn like essentially optimal policies for these tasks. And as far as the final part of my talk, so far we've been primarily using the learned models to optimize a parametric policy, and then we deploy this parametric policy. However, model-based RL has the main advantage of not just having the policy, but also the model, and this model can be utilized further. So learning a parametric policy or a value function is typically called background learning. And this we can loosely think about it as learning a set of habits, like things that we do repeatedly again and again without too much thinking. Like for example, a leisurely walk. On the other hand, we can also use learned models for active mental simulation and real-time action selection. So this is like particularly useful when we find ourselves in situations that are like different from some of the routine. A good example is a game of chess where most of us like mentally simulate multiple moves ahead in our head and actively think about which moves to play instead of like blindly executing some learned policy. So models allow us to do both background learning and online planning, and we can combine the two to get the benefits of both. And we explored this interplay in a project called Polo. Whenever we are acting in the environment, the agent will do a short horizon trajectory optimization by mentally simulating the consequences of different action sequences. This can be done using like a learned world model, for example. And then because we can't look too far into the future, because the set of possibilities can quickly blow up, we will truncate the search horizon up to some horizon h, and then approximate the future with a learned value function. So if the learned value function is like very close to the optimal one, then a one-step look ahead is sufficient. But we can very rarely learn such an accurate value function. And by increasing the search horizon, we can compensate for the errors in the value function. And we can also dynamically decide on the search horizon by looking at uncertainty of the value function and compare it against uncertainty in the model prediction errors. So, and as and when we collect more and more data, we will accumulate all of that data and in the background, keep improving the model and the value function. So here is a demo on like another dexterous manipulation task. The goal is to manipulate the block in the hand to match the desired orientation on the left. And this task can also be compared directly with the Dactyl work from OpenAI, where they use like a PPO algorithm to learn the parametric policy. Based on sort of an indirect comparison, Polo is at least like a couple of orders of magnitude more efficient than PPO, both in terms of samples and compute. And this is again a very complex task due to the large number of potential contexts. Like, what is also very exciting about Polo is exploration capabilities. We can again consider like an ensembles of value functions or models, but unlike what we did in moral, where we were conservative and penalized visiting uncertain regions, in Polo, we can actually reward visiting these uncertain regions. And this combined with online planning component of Polo can allow it to very rapidly explore environments. And I'll illustrate that with an example. So this is a maze environment where there is no extrinsic reward in the environment. And we as the designers of the task know that there is no extrinsic reward, but the agent itself is unaware that there are no rewards. And we would expect that it would essentially traverse the entire maze in the search of rewards before giving up after it has realized that there are actually no rewards. On the left is a pure, in the video, red color indicates regions of high uncertainty and blue color indicates regions of low uncertainty. So on the left is a purely random policy, which results in Brownian motion and a very poor coverage of the maze. The middle agent uses uncertainty in the value function to drive exploration, but uses greedy one-step action selection without any planning component. So the greedy agent actually gets stuck in the maze and is unable to complete it, even though it realizes that there are like still red regions left where the intrinsic potential rewards are high, but it simply does not know how to get to those regions. And as a result, it just gets stuck. The agent on the right is the Polo agent, where we combine uncertainty based like intrinsic rewards with online planning. Because of this combination, it can actually maneuver and go to regions where the potential perceived rewards are high and very quickly cover the entire maze. And as a result, it does not get stuck. And there's like this idea of like essentially uncertainty guided exploration and the importance of planning for exploration was something that we first considered and explored in this particular work. And since then, it has become actually very popular with like many different works exploring different aspects of this idea. So it's a pretty exciting direction on understanding what model-based RL can actually provide for exploration. So with that, I would actually like to stop the talk. There are a few more things that I wanted to discuss, but in the interest of time, like we can probably stop here, and I'm happy to take any questions. And I would also like to thank all my collaborators and advisors involved in all of the different projects. And I'm happy to go over like other aspects of my work in our individual interactions.
Well, thanks a lot, Aravind, for the talk. So I think feel free to ask any questions if anyone has a question. If not, maybe I'll ask a question. So in the game theoretic formulation that you were talking about, essentially it's the exploration exploitation trade-off, right? Where you have the model free learner who is trying to break the model and the model which is trying to, learn about, new states it is visiting.
Mm-hmm.
And so now let's consider like a setup, right? Suppose I end up learning that, like, for example, if I'm driving, right, I should not collide, right?
Yes.
Or my hand is moving in free space, I should not collide. But then when I'm interacting with objects, I must make contacts, which might go against what the model would have learned earlier. So how do you think, we could handle, those constraints where what was unsafe before, right, might end up being much more safer later on, or only the only way of doing it?
I see. So this is like the typical tension between exploration and safety, right? Like, so one approach is like, so offline RL is sort of the idealized case for safety, right? Like all the data is already collected. Yeah. Presumably the collection process was safe, or it may not be, but I no longer have to pay the price because it was already collected. So in that case, like we can really constrain. What that would mean is that either we can solve the task with the available data set, or we cannot solve it. And the only way to make further progress would be to collect like additional data to expand sort of the regions where we have the data. So now the question is like, whenever we venture into unknown territory, like it can either be helpful in terms of improving the quality of the policy, or it can be like really detrimental. And my view is like, it's very hard to pin down like a framework that is broadly applicable for safety, and it might actually be better off considering it on a case-by-case basis, because we can argue like on both sides, which is like, we could say that if I care about performance, then I may have to like interact and I may have to break a few cups, but I break the cup a few times, but then I would not have to like break the cup anytime in the future. Or you could say that I will try my best to like not avoid, like explicitly put in constraints to somehow prevent me touching a cup and breaking it. But then like when I'm deploying it like in the field, like we don't really know, maybe we did not account for all possible constraints or all possible violations, and that might actually incur a higher cost during deployment. So it's a pretty dicey situation, and perhaps like I think the solution has to be like problem specific rather than a general like algorithm level fix.
Yeah, I mean, it's a tough question, right? I mean, that's like one of the most exciting questions to address.
Yes, and it's also so typically in pure reinforcement learning, the view would just be like exploration is good. That's the only way to learn good policies. So if that means breaking a few things, like go and break it. But that's like reinforcement learning. Like when we bring robotics into the picture, or like other applications like healthcare, for example, where like safety and ethical considerations are perhaps even more important than robotics, then this view would start to break down. And then my view is like safety first, and if that means sacrificing on performance, so be it. And that's where offline reinforcement learning is very exciting, because there we can very clearly put in these like, pessimistic constraints or robust constraints, which will force the policy to like essentially stay within known regions. And within known regions, like if there are bad actions, it will obviously prune it out. So the price that we may pay is like, maybe we may not learn the optimal policy, but that's the best that we can do if safety is very important.
Yeah. Well, thanks a lot, Aravind. I think we have time for just one quick question. If not, I think we will, close the talk. And feel free to reach out to Aravind if you have any more questions. So, any last comments, questions from anyone?
Yeah, I've got one. Jumping back to talking about doing this for high dimensional observations, so images, you were discussing rolling out in the latent space. When you learn that embedding to a latent space, you're obligated to throw away some information about your observations. How do you ensure that the policies that you learn are able to make use of the necessary information that's in the observations, and not just what your compression algorithm decides to save?
Yes, that's a good question. So the encoder and decoder are typically trained through like a reconstruction-based loss function. So, for example, let's say it's like something like a robot in a particular scene. In order to be able to recover the next frame, or like 5 frames into the future, the encoder going from the image to the latent state representation better preserve information about like the joint pose of the robot and the different objects, because if that information was not preserved, then there would be no way to actually reconstruct it. So those aspects of the environment that are important for reconstruction will be preserved in the latent space, and other aspects that are not important, for example, like suppose we know that the background is we have like a green screen and the background is always green, then like the notion of green need not be encoded in the latent space and can actually just be encoded in the weights, and like only the joint positions might be there in the latent space, and just with the joint positions we can still like recover the image. Whereas if it was not a green screen and there were like distractor objects, that's the harder case, because then we will be over flooded with information in the latent space, and somehow you have to figure out how to preserve the right information. This like destructors in visual prediction are like a pretty open problem in all of, I would say, video prediction. And like our work is no exception to that. And like we don't really aim to solve that particular problem.
Gotcha. Yeah, I imagine that would similarly be a problem, not just with distractors, but with partial observability. I mean, because you don't have object permanence if you're just predicting, the image, whereas you might need to keep track of something.
Yes, but that can typically be handled because the latent state at time t is not just a function of image at time t, but it is a function of the previous latent state and the current image. Like think of a Kalman filter. We would predict forward and then use the image to correct it. And we can use a similar setup. So historical information that are not available in the current image would still be preserved if it is needed to predict the future. So suppose like an object goes behind like a person and perpetually stays behind the person, then we may not really care about that object. But if it goes behind the person and comes out on the other side, then I better preserve the object-related information to be able to predict the future. And the hidden states will do that.
Cool. Great talk. Thank you.
Yeah. Well, thanks a lot, Aravind. I think we will wrap up now so we do not become too delayed on your schedule. But if anyone wants to chat, feel free to reach out to Aravind and, feel free to set up a time. And with that, thanks again once more and looking forward to all.
Thank you, Pulkit. Yeah, thank you so much for the invitation. And it was such a pleasure to be here and give the talk. Thank you.